Hey everyone, welcome into this example of Calculus 1 on horizontal and vertical asymptotes. So, like I said, this is just a single example, but we are tasked with finding all of the vertical and horizontal asymptotes of this function. The function is f of x equals x squared minus 6x, all divided by x squared minus 5x minus 6. So this is a rational function. And let's remember what the definition of a vertical asymptote is in this context. So we want to try to find the equation of a line, a vertical line, x equals a. So basically we want to find any numbers a, such that the limit as x approaches a of this function f of x is either plus or minus infinity. So this limit is going to tend either toward positive infinity or negative infinity, and maybe depending on the direction that we take the limit, from the left or the right, it could approach either of these for the same value of a. So in order to do this, we first need to decide what are the candidates for a that we want to look at. To do this, we can look at the domain of the function. So we want to try to factor the numerator and the denominator, and we can see here that I've done that. And then think about the values of x, which make the denominator equal 0, because those are not going to be in the domain of the function, and anytime there's a vertical asymptote, we know that that's going to be a point that's not in the domain of our function. So here we can see that x plus 1 and x minus 6, those are the factors of the denominator. So that means that as x approaches minus 1 and x approaches 6, those are going to be the two limits that we want to take for this example. So let's start with x equals 6. The limit as x approaches 6 of this function. To compute this, basically, we first start by taking the limit, and then we ask, okay, what can we do with this, right? Well, we see that we have x minus 6 and x minus 6 in the numerator and the denominator, both, and we really want to cancel those, but remember that we can only cancel them when we're in the limit. So I couldn't cancel them up here. We might have noticed it up here, actually, right? You might have seen this as I wrote out the factored form, but we can't cancel those in the function itself. We can cancel those in the limit, right? And so then our limit just becomes the limit as x approaches 6 of x over x plus 1. And at this point, we can just plug in 6, and we get 6 over 7. So as we take the limit of our function as x approaches 6, we get a number, right? An actual number, and we do not get a plus or minus infinity. So this point is not going to correspond to a vertical asymptote. Actually, x equals 6 is going to be a hole in this graph. All right. Let's take the limit as x approaches minus 1. Well, the only change that we have to make is changing where the limit is tending to, right? So change all those 6's in our limit to minus 1's. All the other work that we did is exactly the same. We don't have to redo that work, right? So we can still cancel the x minus 6. Why not? And then we get to this point where we have our limit as x approaches minus 1 of x over x plus 1. And when we plug into this, we see that we get something that is mathematically not allowed, right? We have negative 1 in the numerator, but we have 0 in the denominator. So negative 1 over 0, this tells us that, okay, this is definitely going to be some flavor of infinity, but for completeness, let's take each of the one-sided limits and try to understand how this function is behaving as we approach x equals minus 1. So we already kind of know that this is going to be an asymptote, because this is negative 1 over 0, of course, is not really 0, right? In a limit, this just means negative 1 over very, very small, which means that in the reciprocal, negative 1 over really small becomes very, very large, right? So let's take our one-sided limit from the left. As we plug in a number that's slightly less than negative 1, when we do this addition, this right here, negative 1 plus 1, we get something that's slightly less than 0. So it's negative 1 over very, very small but negative, and then those two minuses cancel out, and so this limit is positive infinity. And as we take the limit from the right-hand side, so we plug in a value that's slightly larger than negative 1, then when we do the subtraction, we get a value that is very, very small again, right? We're in the limit, so we're never actually equal 0, but we get very close to 0, but this time 0 it's slightly positive, slightly larger than 0. So this ratio is going to give us a negative infinity. All right, so obviously this is going to be a vertical asymptote for us, but we also learned some other information. So we know that as x approaches minus 1 from the left, our curve is going to approach positive infinity, so it's going to kind of have a shape that rides up the asymptote toward positive infinity. And from the right, as we approach from right to left, we're going to approach that asymptote and head down toward negative infinity. Okay, so this function has opposite behavior on either side of the asymptote, but it is an asymptote from both directions, right? Okay, so that's the vertical asymptote. That's the only one. Those were the only two candidates that we had to look at. X equals -1, we got the vertical asymptote. X equals 6, we got not an asymptote, but we got a hole, right? So we found a hole in the graph. So the next question is, can we find the horizontal asymptotes? Because as we know, the question was stated that we want to find all vertical asymptotes and horizontal asymptotes of this function. So let's just first start by remembering what does it mean to be a horizontal asymptote. And that is a horizontal line has the equation y equals something, so y equals b, where the limit as x approaches plus or minus infinity is equal to that value b. So here we already know what limits we need to take. We need to take the limit as x approaches plus or minus infinity. And what I'm going to do is just do one of those two limits for us. So I'm going to take the limit as x approaches positive infinity. You can work through the limit as x approaches minus infinity on your own. It's going to be very, very similar. In this case, remember when we take the limits as x approaches infinity of a rational function like this, we look at the leading terms, right? The leading powers of x. In this case, the highest power of x in the whole function is x squared, right? It's 2. That's the highest power. And it occurs in both the numerator and the denominator, so the powers are the same. And so now we can look at the leading coefficients. So here there were no coefficients, I just threw a 1 in there. If the term is there, it has to have a coefficient of 1. So we throw that in there, and then remember that the limit as x approaches infinity, if the powers are the same on the top and the bottom, then either infinity or minus infinity, that limit is going to be the ratio of the leading coefficients, which in this case is 1 over 1, so just 1. So that's all we have to do to find the horizontal asymptote, and it's the only horizontal asymptote for this function, right? And that's it. So y equals 1 is our horizontal asymptote for this function. So, in summary, we've now found the vertical asymptotes, the horizontal asymptotes, which is one of each, and then we also found a hole in doing. So as I said, we have now found all of our vertical and horizontal asymptotes, and we also identified a hole. So again, in summary, our hole is at x equals 6, our vertical asymptote is the line x equals -1, and the horizontal asymptote is the line y equals 1. So just to finish off this example, let's take a look at the graph and make sure that this all makes sense. So here I've plotted the function f of x. I just plotted it from -2 to 7 because that's the range where the domain, I probably should say, the domain where all of our interesting points are occurring, right? The hole over here is at x equals 6. Here we see that there's something going on at x equals -1. And at x equals -1, indeed, that is our vertical asymptote. So I've plotted that here as a dashed line and made it a different color. Specifically because, remember, asymptotes are not actually parts of the graph, right? That point x, that value, x equals -1, is not in the domain of our function. We can't actually equal -1. X cannot equal -1 in this function, but we can get really darn close to x equals -1, right? We can get as close as we want, and here's what the function does as we get close to it. So it approaches positive infinity from the left, negative infinity from the right. And we also then have our horizontal asymptote. This one tells us what happens as the function gets really far away from 0, actually, as it gets close to positive or negative infinity. We can already see in this plot here that the curve on the right-hand side here is zooming right in. It's getting very close to that horizontal line, right? If we zoom out a little bit so we can get some of the picture on the left-hand side, we can also see that it's doing the same thing over here. So this is the shape of our graph. We have the hole, we have our two asymptotes. And so in this example, we have identified all of the vertical and horizontal asymptotes. We also were able to identify a hole, and then we can look at the graph and make sure that everything makes sense.